So far, we have seen four different ways of specifying the arrangement of components in a system. The first is drawing a reliability block diagram. The second is specify structure function phi of x. The third is specifying the minimal path sets. And the fourth is specifying the minimal cut sets. There is a fifth way to describe the arrangement of components in a system, and it is fault trees. Fault trees are a topic that is not covered in the book, but it is so popular in reliability, it's covered here in the notes. The notion is fault trees are a popular special case of something known as an event tree that gives alternative ways of expressing a coherent structure in terms of the arrangement of the components. Basic events are depicted by circles and diamonds. We'll use circles here. The top event is usually depicted by a rectangle, and OR gates look like below. On the left-hand side is an AND gate, and on the right-hand side is an OR gate. And we'll see on subsequent slides how those are used to specify the arrangement of components in a system. So let's say we have a 5-component parallel system, and here is the reliability block diagram, and we would like to express this as a fault tree. Now, up at the top in the rectangle is something called the top event. And in most application, that top event is the failure of the system. Since we're looking at reliability in this chapter, I'm going to go ahead and instead call it the system functioning. But it can either be the system functions or the system fails. We just choose system functioning here. Well, in this particular system, the system will function when either component 1 functions, component 2, or 3, or 4, or 5 function. As long as one of these 5 components functions, the system functions. So the meaning of this basic event down here, when you see the 1 with a circle around it, that is the same as saying component 1 functions. For a more complicated example, let's look at the 3-component system whose reliability block diagram looks like this. Once again, having our top event be the system functions, the way you read this is the system will function if component 1 and either components 2 or components 3 function. So there is a fault tree which describes this 3-component system. Now, as an exercise here, it says draw the block diagram and the fault tree for a 2 out of 4 system. Well, this is a special case of a k out of n system, and so what that means is we need to use repeated components to draw the block diagram. So starting on the far left here, a 2 out of 4 system will function if components 1 and 2 function. That's one way. Another way is if components 1 and 3 function. Another way is components 1 and 4 function. Got to be organized going through all of these. Another way is components 2 and 3 function. Another one is components 2 and 4 function. And finally, we have made it to the promised land. The system will function if components 3 and 4 function. Now, as always, with repeated components, there are only 4 physical components in this system. However, if component 1, for example, fails, it fails here, here, and here, all at the same time. So repeated components are used to draw the block diagram for a 2 out of 4 system. Now, to draw the fault tree, we start up top with the top event, which is that the system functions. There it is. Now, coming off of there, we're going to put in an OR block. And that OR block will get a plus on it. So here is the OR block. And this system will function. Now we got to come all the way over to the far end here. We're going to put an AND block right here. And it will function if components 1 and 2 functions. That is the first piece up here. Or another AND block if components 1 and 3 function. And you just keep working in this fashion. Or components 1 and 4 function. So we're just going to have 6 AND blocks here. This will be components 2 and 3. This will be components 2 and 4. And finally, the last piece will be another AND block, and you'll see components 3 and 4. So you can see the fault tree uses repeated components in the same fashion that they're used in the reliability block diagram up here. So that is the block diagram and the fault tree for a 2 out of 4 system. If you'd like to see an application of fault trees, you could go to Barlow and Prochon's book. This was published back in 1981. The title of that book, looking it up here, is Statistical Theory of Reliability in Life Testing, Probability Models. Again, 1981 textbook, one of the original and very, very early books. On page 263, their system is an intra-aortic balloon device which provides circulatory assistance to the heart during a surgery. The balloon is synchronously inflated and deflated with the heartbeat, and that heartbeat is determined from an electrocardiogram. In their case, they do have a negative event up top, and that negative event is hazard to the patient. There are 3 ways to get hazard to the patient. The first is balloon inflation during systole, which means the balloon is working against the patient in that case, or electric shock, or the balloon is overpressurized. And in their fault tree, they break it down to other special cases below that on each of those events. Some quick notes on fault trees. They are very effective for group analysis of a system. In fact, if I had a group of people that were not familiar with reliability, I would not use structure functions or reliability block diagrams or minimal path sets or minimal cut sets. I would use fault trees because people think very well and very clearly in terms of these ands and ors. And so it's very, very good for a brainstorming session if you have a system and you're trying to improve it. Fault trees are valuable. Fault trees are also used in something known as failure modes and effects analysis, abbreviated FEMA. There is also failure modes, effects, and criticality analysis, which is FEMICA. And there is a minimal cut set algorithm which can determine the minimal cut sets from a fault tree. Finally, there are things known as dual fault trees, and those can be obtained by replacing AND gates with OR gates, replacing OR gates with AND gates, and for both the top event and for the basic events, replacing occurrence with non-occurrence. In other words, failure becomes functioning and functioning becomes failure. It turns out that the minimal path sets in the dual are the minimal cut sets in what is known as the primal or the original fault tree, and likewise minimal cut sets in the dual are minimal path sets in the primal or the original system. Here is an example of a dual system. If we have this particular original system, and this is what on the previous slide is being called the primal, and we would like its fault tree, we're going to go with a positive event up top, the system functioning, and so here we have an AND gate, here is an OR gate, and finally down at the bottom here is another AND gate. So the idea here is this system functions if component 1 functions and either components 2 and 3 or component 4 functions. That's the way you would describe this system, and that's very easy to see with this particular flow down the fault tree. Now, if we're trying to figure out the dual, notice up front here that we have component 1 is in series with this subsystem. So when we draw the dual reliability block diagram, component 1 is now going to be in parallel with the following subsystem. 2 and 3 in this system are in series. So now what we do is we put 2 and 3 in parallel, and 4 is in parallel with 2 and 3, so now what we do is we put it in series in that fashion, and right there is the dual reliability block diagram. To check one of the bullets before, let's just do, let's go with path sets. What are the path sets for this system? Well, one path through that system is 1, 2, 3. And another path through that system is 1, 4. When you come to the dual system, notice that 1, 2, 3 is a cut set and 1, 4 is a cut set, and those are the only two sets that are out there. So the idea is when you have min path sets for the primal, you get min cut sets for the dual. There is a formula for the structure function of a dual, and sometimes a bar is put above phi, and the formula is phi of x is equal to 1 minus phi of 1 minus x. It turns out both this x right there and that 1 are all vectors, and that's a way you can write down the structure function of a dual. So that ends the discussion on fault trees, and the next section is reliability functions.